All right, topic 3, writing equations for exponential growth and decay. All right, so last time, I made a video, a whole 18-minute long video, and I didn't even have my microphone turned off. But I promise you, this time it's turned on. So let's get it, guys. All right, so topic 3, writing equations for exponential growth and decay. Before we get into that, we need to go ahead and look at this question that we have. So it says a ping pong tournament began with 64 competitors, right? So we have 64 competitors, and it says complete the table, assuming if a person loses their match, they're eliminated from the tournament. All right, so let's think about this real quick. I have a ping pong table, bam, whoa. All right, so we have a ping pong table. It's got your little net, All right, you know what ping pong is, right? I hope y'all know what some ping pong is. All right, bam, a little hit the ball and it's all right, cool. So it's your ping pong table. So if we have one person on each side, right, someone's going to lose. So our competitors after 64, half of them are going to be gone. So now we have, after round 1, we have 32 competitors, right? Yes. All right. Then after round 2, half of those people are going to lose. So we're going to have 16. And after that, after the 3rd round, we should have 18 competitors left. After the 4th round, we should have 4 competitors left. 5th round, we should have 2. And after the 6th round, we should only have 1 competitor left. Meaning, this right here is the winner. Woo. All right, winner. Now, I'm going to write this in a different color so you guys see. If I was to still go, it would have, after 7th round, I would have 0.5 of a person. But that doesn't make any sense, so we actually are not going to even write that because that doesn't make sense to have half of a person. So next, what you need to do is you need to go ahead and graph this and plot the points. I've already done that, so go ahead and pause the video and plot these points and draw this, and then play the video when you're done. Now that I've plotted these points, I have them here. I draw my line, and it's not going to be continuous because this is a real life situation, right? We have 64, and it stops at 1 competitor. So you're going to start it here, end here, and we'll stop it at that. All right, so let's go ahead and answer these questions. So it says, write an equation that best represents the data. Write an equation that best represents the data. So we're going to go ahead and write this equation. Remember, this is our equation right here. Our equation goes in this format. This is exponential form, where A is my initial value, B is your multiplier, right? Also known as your base. It's your base. So let's go ahead and find my initial value. So it's going to be y equals, what's my initial value? I want to find my initial value when my x value is 0, right? Here's my initial value, 64. And then my multiplier, I got to figure out how are these changing by from here to here. What's my multiplier? We're multiplying times 1/2, right? Same from here to here. It's also times 1/2. So that's my multiplier. Bam. All to the power of x, because this is an exponential graph. So now that we have this written out, let's go ahead and answer the rest of these questions. It says, consider the rate at which participants were decreasing. How else can this value be represented? Now they're talking about the 1/2. What's another way to write 1/2? We'll say, if they're talking about a word problem, they'll say half, right? We'll say doubled, or actually not, it's not, that means times 2, sorry, half. Another way to do is 0.50, and we'll do one more, we'll say is 50%. Or we can just say like divided by 2, actually, that's probably the last one. So these are words or ways that we can say half in another way, right? We can say half, 0.50, 50%, or divided by 2. 50% or 0.50, those are important because that's what we're going to be like dealing with a lot today. So what do we have here? It says, when a quantity is decreasing at an exponential rate, what do we call that? We call that exponential decay. And when a quantity is increasing at an exponential rate, we call that exponential growth. Let's go ahead and write those down. Pause the video. Exponential decay, exponential growth. Now, here is the formula for those. Exponential growth is y equals a parentheses 1 plus r to the power of x. Okay, that's exponential growth. Now, decay is the same, except there's a minus sign instead of a plus. Okay, so go ahead and write these down. Now R is considered our rate. So R is my rate. Okay, R is my rate. Now, if this is my rate, one important thing we have to know is your rate is usually going to be given to you in a percentage. Now that it's a percentage, we're going to have to be able to learn how to take, or not learn, we should already know how to do this, take a percentage and change it to a decimal. So let's do like a few practice examples real quick. Let's say I had 50%. What is 50% as a decimal? That's 0.5. Let's say I had 7%. What is 7% as a decimal? That's 0.07, right? So let's say I had 5 as a decimal. So not 5, 5%. How would you write that as a decimal? That's 500%. All right. So that's some stuff we have to know before we get into the actual problems. So again, here are the two growth models we're going to use, or growth or decay model. Pause the video if I'm going too fast, write it down, and then let's get to the next problems. I'm not going to do all these problems. I'm only going to do a few, and then you guys can jump to the homework. All right, so for question 1, it says the population of a city is increasing at a rate. So real quick, it says increasing. What does increasing signify? This right here lets us know that it's growth, right? That's our growth formula. Okay, cool. And what else? It's increasing at a rate of 4%. Here's my rate right here, 4%. What is 4% as a decimal? That's going to be 0.04. All right, so now I have my rate. I'm going to put an R next to that because I know that's my rate. And then we say, in the year 2000, there were 236,000 people in the city. And that looks like that's my initial value, right? This right here tells me where we started, this many people. All right, so this is my A. Okay, cool. It says write an exponential growth function to model the situation, then find the population in 2009. So let's just start with writing the function. So we know it's exponential growth, though it needs to be in this formula right here. It needs to have this model, right? So I'm gonna go ahead and rewrite that. So it's gonna be y equals a parentheses 1 plus r to the power of x. Let's go ahead and write that out because we know this information already. So it's gonna be y equals, which my initial value was, what do we say, was 236,000 people. 236,000, and then parentheses, it's going to be 1 plus my rate, but it needs to be changed to a decimal, so 0.04 to the power of x. Now that I have that, we can answer the question they want us to answer. So here's what it says. And we're talking about each year too, right? So it says find the population in 2009. Now I need you to understand, we're not going to be plugging in 2009 here, okay? Because we need to figure out from 2000, this is where we initially started, how many years have passed to 2009, right? So if I was kind of think about this, right? So if I was to draw a little table out and call this my X and this is my Y, my initial value, right, where we originally started, 0 would be at 236,000 people. And then 9 is what we're trying to find, how many people. But this year, 0 is 2,000. And then down here at 9, that's 2009. So I'm really going to be plugging in x equals 9. X equals 9. That's what I need to plug in. So let me rewrite this, and we can plug in the calculator. Y equals 2 to 36, comma 0, 0. If I add 1 plus 0.4, that's just 1.04 to the power of 9. Plug that in my calculator, and let's see what we get. Sorry. Bam, bam, bam. Do, do, do. Do it that way. All right, so we have 236,000 times, parentheses, 1.04, parentheses, to the power of 9. Press enter. All right, so we have y equals 335,901. And we'll just leave it at that because we're not going to round up half a person, right? So we'll just say this is how much the population would be. Population. And that's it. We have my equation. We've plugged in the value they want us to find, and we're done. All right, so let's do the next one. It says, the population of a city is decreasing, hint, hint, right here, Decreasing, what does decreasing mean? This means it's going to be a decay function, right? It's going to be a decaying function. All right, then at a rate of 6%, how do I write 6% as a decimal? So 6%, what is that as a decimal? That's going to be, we can write 0.06, or you can just write 0.06. We found my rate, which is my R value. All right, then it says in 2000, there were this many people right here, 35,000 people. This is my A value, because this is the initial value they've given us. In the city, write the exponential decay function to model this situation, then find the population in 2012. So let's think about this. My X value, what I'm plugging in is 12, right? Because if the year 2000 was like my zero, my initial value, this is when I originally started, how many years have passed from 2000 to 2012? 12 years. So this is what I'm actually going to plug in once I have my function. All right, so let's go back up to see what the decay formula looks like. It's right here, y equals a, parentheses, 1 minus x to the power, 1 minus r to the power of x. Let's go back up here. Y equals a 1 minus r to the power of x. Let's rewrite that with the information we've been given. All right, so it's going to be y equals, my original initial value was 35,000 times 1 minus, what's my rate? The R value they gave me, 0.06 to the power of x. Now that I have that, we already know we're looking for x equals 12. So I can actually rewrite this, right? Y equals, and I'll plug it in my calculator in a minute. All right, 1 minus 0.06. Oh, I could have solved that. I could have simplified that, but I'm just not going to rewrite it. To the power of 12. All right, get my calculator out and see what we got. That's not what I want. Bring this up here. Bam. So we need to evaluate this for 12. 35,000. Is that right? Yep. Parentheses. 1 minus 0.06. That's not a 6. 6. Close that off. To the power of 12. All right, so what do I get after 12 years? What's my population looking like? We're looking like it's going to increase by 16,657 people, right? Oh, sorry, this is a decaying function. This is not increasing. This is so it's going to decrease by this much people. All right, so that is how we use our formulas for growth, or how we use it for decay. Now, we're going to answer these few questions, 3, 4, and 5, and we'll just jump to the last one, okay? Stay with me, guys. Stay with me. All right, so here's what this one says. For each equation below, identify the exponential growth or decay. That's the first thing we need to do. Identify the initial value. That's the next thing we're going to do. And then we need to identify the rate. That's the third thing. All right, so the rate is the third thing. All right, so here we go. Step 1, is this growth or decay? Here's how we know. If this value that is, where the x is, right under it, this value is a positive number. I'm sorry, not positive. If it's greater than 1, it's a growth. If it's less than 1, then it's decay. So we know it's a growth, right? It's the growth. And then we need to identify the initial value. That's going to be 3.34. And we actually need to figure out what was the rate. 1.67 was not the rate of growth. Remember, my formula looks like this. Y equals a parentheses 1 plus r to the power of x. My rate was this number that I added to 1 to get this here. What number did I have to add to 1 to get 1.67? It's pretty obvious. I needed to add, right, 0.67. But let's write it as a percentage. This is also known as 67%. Bam. That's it. Next one. Number 1. All right, this value right here is less than 1, so this is decay. All right, 2, what's my initial value? Easy peasy, 8. And 3, we need to figure out my rate. Remember, if this is decay, my formula is this. Y equals a parentheses 1 minus r to the power of x, right? So again, I have to ask myself, what did I have to subtract from 1 to get 0.54? I had to ask myself that. What did you have to subtract? You had to subtract 0.46, right? Which is also 46%. All right, last one, and then we have one more problem. Again, this is a positive 4. Well, it's a 4, which is just greater than 1, so we know this is growth. Excuse me, 2 is my initial value, 4.5, easy. And then 3, again, if this is growth, it's y equals a parentheses 1 plus r to the power of x. So you ask yourself, what did you have to add to 1 so that when you add, you get 4? Well, it's 3. But what is 3 as a percentage? It's 300%. It's a lot of growth there, man. It's a lot of growth. All right, so that is how we do questions 3, 4, and 5. The last question that we're going to be doing right here. So it says, use the data table to write a function that models the data, then describe the decay rate at which the cells are decreasing. So the way that we're going to do this first is we're just going to write it in the normal form that we know, because it doesn't give us it doesn't give us the rate of decay or the rate of decay. We have to find it. So here's what we're going to do first. First, we need to put it in this form right here. Y equals a times b to the power of x. All right, we already know a is initial value, so that's going to be a, what is it going to be, 20,000, sorry. My b value is my multiplier. Now, for me, I can't figure out what is being multiplied from here to here to get to this. I don't know. So if you can't easily tell that, remember your b value, to find it, you take your new y value and divide it by an old y value. So what I'm going to do here is I'm going to do 19,000 divided by 20,000. Now, when you do this, you should get, it's probably like 19 over 20, but that as a decimal should be 0.95. So I just found my b value, right? I'll leave it as that. So 0.95 to the power of x, right? Now, again, this right here isn't my decay rate. This isn't my decay rate. Just like the problems that we just did, I got to figure out, if this is decay, remember my function, my model for decay is this, 1 minus r to the power of x. What was this rate that when I subtracted it from 1, I got 0.95? Well, that's kind of easy, right? It's just 0.5, not 0.5, sorry, 0.05. 0.05. Now that as a percentage is 5%. So your decay rate is 5%. Bam, bam, bam. That's it, guys. All right. So go ahead and go to the homework. I hope you enjoyed this video. I hope it was straightforward and easy. Have a good day.